Hello children, in this video we are going to prove that square roots of prime numbers are irrational. What are prime numbers? 2 is a prime number, 3 is a prime number, 5, 7, so on. These are prime numbers. So we are going to prove that any prime number square roots like root 2, root 3, root 5, etc. are irrational. So let us assume that P is a prime number. Let P be any prime number. P be any prime. And so root P, we'll have to find whether we have to prove that root P is irrational. So what does it mean? Irrational is it cannot be written as a ratio of two integers. That is, root P cannot be written as A by B. It cannot be written in this form, A by B. So let us prove this by assuming the contrary. That is, we will assume that let root P be a rational number. That is, let us assume that root P is a rational number. It can be expressed as A by B. It can be expressed as a ratio of two integers. Here we will consider A by B not having any common factors. A and B do not have any common factors. That is, if rational numbers can be represented as a ratio of two integers, so we can, if there are any common factors in the two integers, we can cancel them and reduce and write it in the simplest form, which is called the irreducible form. This is irreducible. That is, whatever common factors were there, both the numerator and the denominator were divided by these common factors, and the final ratio which is obtained is A by B. So A by B does not have any common factors other than 1. So this is very important. I am saying it again and again because this that A by B has no common factors other than 1 is very important in our proof. We are assuming that this A by B are co-primes. So they are co-primes, irreducible. So they all mean the same. So our assumption is this. Now let us see where our assumption leads us to. So let us, because we cannot do much of working with the square root of P, let us try squaring both sides of this equation. Root P the whole squared is equal to A by B the whole square. We're just trying to manipulate and see what we are going to achieve. So P is equal to A squared by B squared, or if you multiply both sides by B squared, you get B squared P. B squared P is equal to A squared. So A squared can be expressed as a product of P, a prime number, and B squared. So B squared is an integer. It's an integer, it's a positive integer because it's square of an integer. So this is an integer and it's being multiplied by P. So P is a factor of A squared, or can we write it as A squared is a multiple of P. This is what we are finding out from this. A squared is a multiple of P. Now does this mean anything for A? If A squared is a multiple of P, does it mean that A is also a multiple of P? Let us explore. Now A can be expressed as any composite number, any integer can be expressed as the product of its primes. So can we express A as f1 into f2 into f3 into so on till fn? These are all, consider that f1, f2 are all primes. So fn is the nth prime number. So it is a fact. All these are factors of A. So suppose all these are the factors of A, then A squared will also have the same factors. A squared is nothing but A multiplied by itself. So the factors also would be the same. So f1 into f2 into so on, multiplied by the same factors again. Being the numbers being the same, a and a. Factors also are the same. Or I can rewrite this as f1 into f1, f2 into f2, and so on till f1 into fn. Now p being a factor of a squared, p has to be somewhere over here, somewhere among these factors. So let us assume that f1 is p. If you assume that f1 is p, this f1 is p. So if f1 is present in a squared, then f1 is present in a also. That is, p is present in a. So if a squared is a multiple of p, it implies a squared is a multiple of p implies that a is also a multiple of p. Is also a multiple of p. Now, so we can express a as some integer into p. Because a is a multiple of p, we are expressing a as some integer into p. So squaring both sides, so that we are squaring it because we can compare it with this equation which we have already obtained. So what do you get if you square? You get a squared is equal to k squared p squared by squaring both sides. Or we already know that a squared is equal to b squared p. So let us compare both of them. K squared p squared can be equated to b squared p, or dividing by p on both sides. Can I write? So I'll just rewrite this equation for you. K squared p is equal to b squared p. Sorry, this is k squared p squared. Now dividing both sides by p, you get b squared is equal to k squared p, or in other words, b squared also has p as its factor, or b squared is a b squared is a multiple of p. B squared is a multiple of p, which implies that b is also a multiple of p. Just by the previous argument, if b squared is a multiple of p, then b is also a multiple of p. So, have we arrived at a contradiction? Yes, we have. We say that a is a multiple of p, and we also say that b is a multiple of p. But what was our assumption? Our assumption was that a and b do not have any common factors, isn't it? This was our assumption, but now we have a contradiction that at least one factor is common, that is a is also a multiple of p and b is also a multiple of p. So this is not the irreducible form, and they are no more co-primes. Whatever we assumed a by b as co-primes, it's been proved that they are not co-primes. So this proves that our assumption is wrong, and hence p is a root p is irrational. We are assumed that root p is rational, and that is why we have obtained all these absurd logical, not logical, illogical conclusions. So root p is irrational. Thank you.